Okay, so now we start the next chapter. I will teach you a little bit about from the next chapter, and then we will have the exercising sessions next week. You can practice, and then we will have the test, and then the rest of it we will continue. Okay. So this is more or less, again, what I want to teach today. It's already covered in Math 3C, almost all of them. Okay. But I just want to refresh your memory about what you have already learned. So you know that the main topic here, we want to be able to draw the graph of a function as precisely as possible. Okay, and then you know that in principle there are infinitely many points on each graph. Of course, if we were able to find all the points on the graph, then of course it was easy. Just we highlight those points on the display, or we can do it with pen so that the graph of the function is automatically being is drawn. Yes. But the point is that because there are infinitely many points on the graph of any function, it is not possible in practice to find all infinitely many points on the function so that we can have a very precise form of the graph of the function. So if you want to have a better and more precise version of the graph of a function, we need to have some ideas how we have to do this. So let me make this a little bit clear here. So for example, assume that you want to draw the graph of y equal to x squared. Of course, this is a very simple function. You already know the graph, but assume that you want to draw the graph of the function. The first thing that comes to mind is to just find the points which are sitting on this graph by giving numbers to the x and finding the values of y and finding those points on the coordinate system. Yes, for example, you can set up a table something like this. You can say that, okay, this is my x value, this is my y value. I put -2, I get 4. I put -1, I get 1. I put 0, I get 1. So what I am doing, I am putting these values inside this formula and then square them. This is my y value. Yes. Oh, sorry, that last one is mistake. It is 0. And then, for example, if I continue this a little bit more, then you get 1, you put 1, you get 1, you put 2, you get 4. And of course, you see that if I really want to have a precise form of the graph, it is not possible by doing it like this, because when I go from 0 to 1, there are infinitely many points between 0 and 1 that I am ignoring. Okay? So you might think that, okay, is it possible at all to draw the graph of a function in a fairly reasonable way? Okay, the answer is yes, and and then you will see that we need to use the notion of derivative to be able to draw a very nice and qualitatively precise form of the graph of my function. But let me just tell you what is the practical point here. So assume that you really want to draw the graph of this function just using these points. So what you do is this. What we can do, we can find these points. So I'm just finding -2 and 4. So it is -2, 1, 2, 3, and 4. So -2 and 4 is this point, and then I have -1 and 1 is this point. Then I have 0 and 0, it's this point, and then I have 1 and 1, it's this point, and then 2 and 4 is this point. Okay, but might be you know that the graph is something like this, but you know that this is not 100% guaranteed because of these points. Yes. The reason that you know that this is probably the correct graph is that might be you have seen it in the books, or you have used your calculator or any software to draw the graph of this function. But in principle, just having these numbers, it means that, of course, yes, these are the points that I am 100% sure that my graph is supposed to pass through. Yes. But what is the reason that I am drawing it in this way? Might be, we don't know. Might be this is the case that from here to here I should come like this, and might be this graph goes up and down and then reaches here. I don't know, this goes here and then something like this. So who knows that the graph is not something like this? Of course, you might say that, okay, if I want to show that the graph is not this, I can choose another point between 0 and 1, for example, say 1/2, and then when I calculate it is 1/4, and then you say that, okay, if you take 1/2 and 1/4, it lies on this green one, not on the red one, so it seems that this is not the case. But again, I can, you see, I can just find that point. I can go from here to here and then just go with the other way around. So I mean, I hope that you understand that it doesn't matter how many points I provide. There is no guarantee that I am drawing the picture which is close to the real graph of the function. If I want to only follow putting points into the formula of the function and find the corresponding y values and highlight them on my coordinate system. Yes. Okay. This is something very important. So we want to understand why this is not happening, for example, for this graph, why this green graph is reasonably a good picture to the real graph of this function. Okay, so for example, if you see the difference here, you see if I have this situation or this situation, there is something important. If I have this situation, the graph is bending downward. But if I have the green one, the graph is bending upward. Okay, so that is one qualitative quality on the graphs that are important. And then we will see that what is, or how we can understand them from the function points of view. So by the way, let me just repeat that. What I have in my hand is the formula for the function. And I don't know anything about the graph of the function. I want to use my math knowledge to be able to draw the graph of that function, okay? So one thing that is important is that, okay, if I have these 2 points, should I connect them in this direction, in this way, or should I connect them in this way? So it is important that if the curve is bending upward or if the curve is bending downward. So that is one thing which will enable us to draw a better graph for our function. The other point is the turning points, yes? So for example, let me consider a graph like this here for you. Let me clean this, make it bigger. Yes. So assume that you have this graph of this function. For example, it goes here and then it comes back, and then for example it goes, let me make it better, so I don't know if this will work or not. No, it's not working. So if I keep it, it does not work like that. Okay, so let me just do it quickly. Okay, so something like this. If I ask you, for example, assume that this is the graph of the function that you have, y equals to f of x, and then which points are more important for you if you want to draw the graph of this function? Which points are more important than the other points in this graph? So if I tell you that I will give you the points on the graph that you like it, which one do you prefer to have a better picture of this graph?
The local maximum and minimum points?
Yes, the turning points, yes? Because if you know that these are the turning points, so this is not the turning point, sorry. This one, this one, this one, and this one, this one, and this one. These are turning points. So somehow, if I give you these points, somehow you can connect them. At least you know that the function should go back, so the turning point. And of course, the turning points are of 2 types. One of them are minimum types. So it means that the function around that point, the graph of the function around that point are higher than the point itself. And sometimes the graph of the function around that point are lower than that point. So if I know that this is a turning point of the lower type, of the higher type, so it should be, I know that around that point, the graph looks like this. And if I know that this is a turning point where it is a minimum, it is a lower one, then I know that at least around that point, the graph looks like that. Of course, it might be very sharper or it might be very wider. But in general, the quality, from qualitative points of view, the graphs are the same. So the turning points are very important for us. And these points are also important because you see here, this point, before that, the function is bending upward. Then immediately after that, the function is bending downward. Okay, so this point is called an inflection point, a point at which the concavity, bending upward or downward of the function. So that's called concavity, yes? Or sometimes people call it convexity. Okay, so the way that the curve bends, either bends upward or bends downward, is also important for us to have a qualitative picture of the graph. And it is also clear having the turning points is also important for us if we want to have a better and a qualitative picture of the graph. Okay? But let us see, how can I now go back to this idea that, okay, the function, the rule of the function is given to you, not the graph of the function. Because if I give you the graph of the function and I ask you where is the turning points, you can immediately point these points for me. It is not a big deal, yes? And if I ask you what is the inflection point, you can immediately see that, for example, this is one inflection point. This is also another inflection point. Why? Because before that, the curve is bending upward, and after that, the curve is bending downward. So don't lose the logic. If I give you the curve and I ask you these questions, they are super simple questions. Okay? The point is that I do not have the graph of my function available. I have the rule of my function available. Using the rule of my function and the notion of derivative in some way, I want to be able to draw a qualitatively precise, reasonably precise graph of my function. This is the logic that should be in the back of your head, okay? Okay, so let us first concentrate on these points. So let me tell them officially. So where this point here, you see, let me change the color. This point here is called a local maximum point. Local maximum. Why we say local maximum? First of all, why we say maximum? Because it is clear that this is higher than the points somehow. But why we say it's local? Because it is, even though it is higher than the points around it, but it is still lower than this point. So I cannot say that this is the maximum of the whole function. This point is locally maximum. It means that if I compare the heights of this point with the points in the vicinity, in the neighborhood of this, all these lines that I am drawing are shorter than this line, which corresponds to that point. So this is the meaning of having a local maximum at that point, at a point, yes? And then, for example, what is another local maximum? This is also a local maximum. What is another local maximum? This is also a local maximum. And then what are the local minimum points? So this is a local minimum, yes, for the same reason. It is locally minimum. It means that the height is lower than the points in the vicinity of that point. But of course, you see that this point is even lower. But this means that this is locally minimum. This point is also locally minimum. Yes, this point is also a local minimum. And something interesting that happens, this is also something, I hope that this picture is not exact, but you can see that this is, even though this is a local maximum, you see, this line, if I just continue it, this point is a local maximum, but it is still lower than the local minimum. So I want you to fix this. Yes, if I talk about maximum of a function and minimum of a function in the whole range, always maximum is greater than or equal to the minimum value. But when I am talking about local maximum and local minimum points, then you need to correct this in your brain. If you think in that way, you see this local maximum, the height of this local maximum, the value of this local maximum is this. The value of this local minimum, even though this is minimum, it is still longer than this one. So the local minimum value is higher than the local maximum value. So this can happen for local minimum and maximum points, not for absolute maximum and minimum points, not if you see the whole picture. Is that clear? Okay. Now, intuitively, how do you think we can locate these turning points? If I give you the formula for the function, you might remember something from Math 3C. And then, of course, even if you don't remember, this picture somehow tells you what are the possible candidates for these points. Do you remember something, or you can cook up something here right now for me? How do you think I will be able to find these local maximum and minimum points? Because we realized they are important points if I want to draw the graph qualitatively. And then how should I find them? Do you have any idea?
We find the points where the slope is 0.
Why? Can you tell me geometrically why these are reasonable points?
Because then it means that there are either points nearby which are all below that point or above that point.
No. You said that the derivative should be 0. Yes, the slope should be 0. Why? Yeah, the reason is that, yes, if you draw a quality, I'm just intuitively saying, because if I draw a tangent line here at local maximum point, because of the nature of the local maximum, what you expect is that this tangent is horizontal. And if the tangent is horizontal, if this point is point A, if I ask you what is f prime of A, you would say that this is 0. Okay? And the same thing happens for local minimum as well. The local minimum here, assume that this is B. In the local minimum, if I draw the tangent to the graph, it becomes horizontal by the nature of the local minimum point, yes? And then, because the tangent is horizontal, it means that the derivative at that point is also 0, because the derivative at the point gives you the slope of the tangent line. On the other hand, we see that the line is horizontal, so the slope is 0. So if I ask you what is the derivative at this local minimum, you will also answer that this is 0. Okay. And then the same thing happens here, the same thing happens here, the same thing happens here. Even right now, I have problems. Can I tell that, okay, I take the derivative and put it equal to 0, and what I find is local maximum or minimum points? This is one possibility that comes to mind, because I see that, okay, if I want to find the local minimum and maximum points, at all of them, it seems that the graph is, the tangent line seems to be horizontal. Okay? So one possibility, one thing that comes to mind might be is this. I take the derivative of the function and equate it to 0, and then I find the answers. Those answers are local maximum and minimum points of my function. Corresponds to local maximum and minimum points of my function. Even if this is true, then still I have a problem, because I don't know which one corresponds to the local maximum and which one corresponds to a local minimum. Okay? But still, this is not 100% correct either. So I cannot say that. Do you think I can say this? I take the derivative of f of x equal to 0, and I get, for example, some answers, x1, x2, x3, and etc. Can I make sure that these numbers corresponds to either a maximum or a minimum point?
No,
There
because
is one
they could be inflection points.
horizontal. Yes, that is called a terrace point. So let me draw another tangent line here for you. If I draw the tangent line here, this is also horizontal. I didn't draw it very carefully, but hopefully you understand what I mean. If I ask you what is the slope of the tangent line at this particular point C, you will answer again f prime C is equal to 0. Okay, but is this point a local minimum? No. Is this point a local maximum? No. So that is, I am facing two problems. In order to find the local maximum points and local minimum points, by the way, these are called local extreme points. Okay, when I say extreme, I mean either maximum or minimum. That is a short way of saying maximum or minimum. Okay, so when I take the derivative of my function and I equate it equal to 0, I will get a set of numbers in front. The problem is that these numbers are just candidates for local extreme points. Yes, because some of them are fake ones. It might happen that the graph of my function is of having some point like this, then C will appear in my list, but C does not correspond to a local extreme point. Okay? This is one problem in front of us. Another problem in front of us is that even if these numbers corresponds to a local extreme point, we don't know which one corresponds to a local minimum and which one does correspond to a local maximum. Okay, so is the problem clear? So my goal is to be able to find the turning points. Why? Because turning points are important points if I want to draw the graph of my function. Okay, so the first question is that, is it possible to locate these points using only the rule of my function, which is the only information available for me regarding a function? The first investigation shows that there are points that I need to be careful about them, because I was convinced that at least at all these local points, I have a horizontal tangent line. Horizontal tangent lines corresponds to derivatives equal to 0. But can I say that, okay, you give me the function, I differentiate it, and I equate it equal to 0, then I will get I will get numbers, I will get x coordinates corresponding to local extreme points. Immediately, this picture shows that no, this is not the case. Because at least you see in this graph, you have a point at which the derivative is equal to 0, but the point does not correspond to a local extreme point. So that is one problem in front of me. Another problem is that even if this is not happening, I get some numbers. I get A, B, C, for example, D, and etc. I don't know, if I don't have the graph in front of me, I need to know how should I understand which one corresponds to a local minimum and which one corresponds to a local maximum. Okay, so do you remember how can we do this? So the first step that seems reasonable is to take the derivative and then, take the derivative Step 1. Step 2, equate it equal to 0 and get some number, for example, x equal to a, and etc. I would say that these numbers that you see are only candidates for local minimum and maximum points. There might be a fake one in front of, in between them. How should I find the fake ones so that I can drop them from my list? And how should I realize which one of these points corresponds to a maximum and which one corresponds to a minimum? Do you remember how did you answer this question in Math 3C?
Maybe we calculate the derivative like immediately before and after those points and see if they're like the value, is it increasing or decreasing?
Exactly, exactly. So let us see. Let us understand the difference between the nature of these 3 points. Let us concentrate on a local maximum and a local minimum and this point. This point, by the way, is called a terrace point. Okay, so let us concentrate on these 3 points. What is the difference between these 3 points that can highlight something for me so that I can distinguish them when I calculate this? If you look at the maximum point, you see that the function is going up. When it reaches to maximum, it immediately turns down, yes? It goes up and it increases, and then suddenly after that, it decreases. In the minimum case, this is the other way around. The function is first decreasing, and immediately after that, it starts increasing. But in a terrace point, the function is going down, and still after that, it is also it's still going down. So decreasing and decreasing. Okay, of course, you might have a terrace point like this. You might have a function increasing, and after that, again, increasing. So this is the main property that I can realize. I can use it to locate a terrace point, to differentiate a terrace point from a local extreme point. Yes? In a terrace point, the function before the point and after the point has the same nature. It decreases all the time or it increases all the time. But for a local maximum point, the function goes up and then goes down. And for the minimum, it goes down and then after that goes up. Okay, so this is a very important feature that differentiates between these points geometrically. But how can I understand this from analytic point of view? How can I understand my function is increasing? Again, remember, you don't have the graph in front of your eyes, you just have the rule for the function. How do you understand that the function is increasing? By having the rule of the function. And how do you understand the function is decreasing? Do you remember?
If it's increasing, then the slope is positive, and if it's decreasing, the slope is negative.
Exactly. And that's the exactly geometry. This is the way that I am telling you. Of course, I can teach you in a way that you can memorize it, but I want you to understand. So if you see all these parts, for example, where the graph is increasing, let us see something in common in all of them. Let us take this point randomly, and I draw a tangent line. Is that the slope of this tangent line positive or negative? So hopefully you remember that if you have a line of this form, the slope is 0. If you have a line of this form, the slope is positive. And if you have a line of this form, the slope is negative. And of course, if you have a vertical line, a slope is not defined, yes? Undefined, let me write. So this is something that you need to know. Okay, so now let me take this random point. You know that here the function is increasing. Let us choose one point on this portion of the graph and draw the tangent line. You see that the tangent line is of this form. So the slope here is positive. Okay, let us go to another point. The slope is still a slope is a little bit smaller, but it's still positive. Let us go here and I draw the tangent line. The slope is even smaller, okay, but the slope is still positive. So this positiveness of the slope is a feature of this part of the graph, which the graph is increasing on that portion. And when I go to the decreasing part, if I do the same, you see when I draw a tangent line, the tangent line is of this form. So it means that the graph is decreasing. Sorry, the slope is negative. And if I do this here, again, the slope is negative. So this is one thing that immediately it becomes clear from this geometry, yes? This tells you that if the graph is increasing, the slope, or in other words, the derivative should be positive. And if the function is decreasing, the slope, or in other words, the derivative should be negative. So you see, if I want to write something roughly here, I would say that here on this portion, the derivative is positive, but here the derivative is negative. So I can immediately realize which one of these points that I get here corresponds to a local minimum. To understand that, I need to determine the sign of my derivative before number A and after number A. If the derivative before A is positive and after A it is negative, so it is a maximum. Now concentrate here. If the derivative before that is negative and after that is positive here, then it means that this is a local minimum. So it means that at local minimum and maximum, the sign of my derivative is changing. For maximum, it changes from positive to negative. For minimum, it changes from negative to positive. But if I want to see about the terrace point, here you see the function is decreasing. So it means that the derivative is negative. Here still the derivative is negative. So you see that the sign of derivative is negative, still negative, doesn't change. For this type of terrace points, if I draw this, the derivative is positive because the function is increasing. After that, the function is also increasing. So the derivative is still positive. Yes? So this is what will help us to specify the local maximum points and minimum points of a function. So if I want to talk about this algorithmically, I would tell you that you take the derivative, you equate it to 0, and then you find the numbers from this equation. At this stage, there is no guarantee that these numbers that you get here correspond to a local extreme point. These are just candidates for those points. So it means that if this graph is supposed to have a local extreme point, those are among these numbers that you get. Some of these numbers might be fake ones. It might happen that this is happening here. And the other question is that if they are not fake ones, which one corresponds to a max, which one corresponds to a mean? These are the questions that we want to ask. And this is a theorem in mathematics that what I described here, which was geometrically very clear, is the content of a theorem that we call it the first derivative test. Okay, so let me write this content here for you. The first derivative test. Okay, so what should I do? How should I collect? By the way, let me give you, let me mention here, there are harder functions like this. You see, in the functions that I have drawn here for you, I am considering two essential things. One of them is that my function is continuous. So it means that I can draw the whole graph with one pen stroke without raising my pen and put it back. So my function, so this is, if the function is not continuous, that is higher than the level of this course. You will study it later in the university, okay? So that is one thing. Remember, when I am talking in this chapter, unless explicitly mentioned otherwise, I am always assuming that my function is a continuous function. It means that the curve the graph of the function can be drawn with one pen stroke. This is something that you always assume. So remark. So we assume that 1, the function is continuous. 2, the function doesn't have any sharp points. The function doesn't have the graph of the function. The function doesn't is differentiable. Let me write it in this way. Let me write it in this way. The function is differentiable everywhere. So do you remember what I told you about differentiable? It means that there is no sharp points and there is no points at which the tangent line is a vertical. Yes, so you shouldn't expect having something like this. You shouldn't expect having something like this. This is a sharp point. I don't know. This is a sharp point. This is a sharp point. So I am not talking about the functions whose graph have some kind of one of these behaviors. So no sharp points. And then I am not considering the functions something like this at which when I draw the tangent line is vertical. Okay? This is not explicitly mentioned, but the book is always talking about these type of functions. Yes? This is very important to understand. So let me write this here, to put it in a box here. So whenever we are talking in this chapter, we are talking about the functions that are continuous everywhere and they are differentiable everywhere. Continuous means that I can draw it with one pen stroke. Differentiable means that I do not have any sharp points. I do not have any points at which the tangent line is vertical. So have it in the back of your head. Because if this is the case, this theorem still is true, but I need to change something in it a little bit. Okay? Okay, so the lesson I talked a little bit because I really want you to understand this picture. But if for solving problems, you just need to know how to use the first derivative test, which is the content of the lesson. The first thing that you do is this. Determine f prime of x. Number 2, solve f prime x equals to 0. Let x be equal to a is an answer, be an answer, be a solution. Okay, number 3, you need to set up a table, set up the sign table. But now, hopefully, you don't need to memorize anything. You can just visualize this picture in your head. You immediately understand what's going on. Otherwise, you need to memorize that. So what is the thing we have to do? There are 4 possibilities, yes? And this is a standard, even in your book. The sign table consists of 3 rows. The first row corresponds to x value. The middle one is the derivative. The last one is the function itself. Okay, what you do, you take this value that you got and put it here. Of course, you put derivative equal to 0 and you got a, so it means that if I put x equal to 0, the derivative becomes 0. And if I want to find this value, the value becomes f of a. And what you do, you determine the sign of the derivative before this point and after this point. Before means all x's is smaller than a. After that means all x's greater than a. It might happen that on the left-hand side you have negative and on the right-hand side you have positive. When the derivative is negative, based on that picture that I gave you, the function goes down. And then if the derivative is positive, the function goes up. If this happens, If this happens, you can immediately conclude that the point A and f of A is a local minimum. Yes, it is not hard. It goes down and then goes up. You see, it is like a minimum. It might happen that I have this scenario, yes? It might happen that I have this situation. I have x, again, I have f prime of x, I have f of x, but this time when I put a, of course, this is again 0, this is f of a, but this time this becomes positive, this becomes negative, then it goes up, and then it goes down. So the point A and f of A is a local maximum. And it might happen that I have these two cases. So x, f prime of x, f of x, x, f prime of x. Let me make it clear. F prime of x and f of x. It might happen that I have this situation. This is negative. This is again negative. So it goes down, it goes down. Or if I put here, this is positive, this is positive, it goes up, it goes up. In both cases, A and f of A is a terrace point. So if someone asks you what is a terrace point, you would say a terrace point is a point at which the slope is 0, the slope of the tangent line is 0, but it is not a maximum nor minimum. Okay, so this is what you need to know very good. Okay, it is long, but I think if you imagine it in this way that I told you, you can immediately get it back from your memory when you need it. Okay, is there any question here? Okay, so let us solve some problems to see how it works in practice. And this is important. There are two tests. This is just the content of the first derivative test. There is also another test. It's called the second derivative test. I will come back to it later, okay? So let us solve this one. From all the discussion that I introduced you today, you should be able to solve this problem. If you can solve this problem, it means that you are completely on the safe side. So let me write example. Determine and classify all extreme points of the following functions. So number one. So let me give an example that can be given exactly in Math 3C. So this is not something hard. X to the 3 minus 3x squared minus 9x plus 5. First of all, I hope that you understand. I am supposed to determine all extreme points, maximum and minimum points, and classify all of them. I want you to tell me which point that you found is maximum and which one is minimum. This means classify the points. Okay, so what should I do? The first step you see here, I want to use the first derivative test. I determine the derivative, I put it equal to 0, I find the answers, then I set up a table. That is called the sign table. Yes, that is what I have to do. I don't know what is this. Okay. So I do the same thing here. I take the derivative first. It becomes 3x squared minus 6x minus 9. I equate it to 0. So this tells me that 3x squared minus 6x minus 9 is equal to 0. Of course, you can start solving it immediately, but I see that this is divisible by 3, all of them. So I divide by 3 to make it simpler for myself. And then if you solve this, I don't solve this equation. I can factorize it, by the way. I don't think at this level you should be able to factorize it immediately. I need two numbers whose sum is -2 and the product is -3. What are those numbers? One of them is -3, the other one is +1, yes? If I add them, it becomes -2. If I multiply them, it becomes 0. Of course, you don't have to do it in this way. You can use PQ formula, okay? So then you get that x is equal to, let me write them in, let me write this, x equal to 3. This is one answer, and the other answer is x equal to -1. Now, please answer these questions for me. Okay, is it guaranteed now that I have, this function has local extreme points right now?
No, because
No,
they
it is
could
not.
be.
Yes, because these could be fake ones. But I can say, can this function has 3 local maximum points?
No.
No, because the candidates are 2. So it means that even if both of them are not fake ones, then I have at most 2 extreme points. But is it guaranteed right now that I have 2 extreme points? The answer is no. Okay, even if they are extreme points, which one is corresponding to a minimum, which one corresponds to a maximum is not clear yet. So this means that I have to set up the sign table to answer the last part of the question. So what I do, I will take this sign table. You remember the first row is x, the second row is f prime of x, the third row is f of x. And it is very important when you want to put these numbers in the first row, it should be written in order from the left to the right, smaller to the bigger, yes? So I would write -1 here and then 3 here. Then, by the way, in the book, they have written, I don't know, between -1 and 3. You really don't need to do that, okay? So what I mean on the left-hand side, it means all values is smaller than -1. This means all values greater than 3, and this means what is between -1 and 3. So you really don't need to make it so big. And then immediately below these two, I can put 0 here and 0 here. Why? Because I myself put the derivative equal to 0, and I got these two answers. So it is clear that if I go back and put these two answers in the derivative, the answers are 0. This is why we put 0 and 0 here and there. But when I want to answer what is this one and what is this one, you see this row is the f row. So whatever I want to put here, I need to go and read the information from my function. So it means that I go in the scratch paper, or I can just write it here in the margin. So here f of -1, it's -1 to the 3, -3, -1 to the 2, -9, -1, and then I have +5. So it is -1, -3, +9, +5. It's 14 is 10, yes? So what I put here is 10. Okay, and then I go here. I put 3 here, so f of 3 is this one. I put 3 minus 3 times 3 to the 2 minus 9 times 3 plus 5. It's -22, yes? Okay, something that I want to mention, of course, in principle, now you need to know the sign of your derivative in these regions. So I want to know that if the derivative is positive or negative. The trick is to do this, and this trick works because the derivative is continuous. Okay, so that is the remark that I mentioned here is very important. So the derivative here I mentioned the function is continuous. If I want to be very precise, I should say that the derivative is also continuous. But the derivative is continuous because I have already mentioned that the function doesn't have any sharp points. If the function doesn't have any sharp points and itself is continuous, its derivative remains continuous. Okay, so here, if I want to know the sign here, what I do, I choose a random number here. But of course, -2 is the better one. Yes, -2 is lower than -1 and is the smaller number, so I can manage it in my head. Yes, then I go to my derivative. Be careful, don't go to your f. This is the line for derivative. You go here and replace x with your random number -2, and let us see what happens. So f prime of -2, for example, is 3 minus 2 to the 2 minus 6 times -2 minus 9. Yes? Is this positive or negative? So it is positive. If it is positive, everything here would be positive. This is a little bit strange. You are saying to me that, okay, I'm telling you that you just check a random number in this area. And if it is positive, it guarantees that every other number that you choose here is also making the derivative positive. The reason is that the derivative is continuous. If this is not the case, this is not always possible. And then you don't need to be worried about that. So this method is enough for your case. But if someone asks you why this is correct, you need to understand that this relies on the continuity of the derivative. Okay? Of course, that is not very hard. I can discuss about that later if that's interesting for you. But just try to learn the trick. You take a random number in that one, the one that you can do it easily, and then put it in your derivative. If it is positive, then you need to make sure that you make sure that everywhere it is positive. Don't worry about that. And if it is negative, it means that everywhere in that interval it is negative. Okay, now go here. Which number is good to choose? 0 is the best choice. Calculation with 0 is simple. Yes, between -3 and -1 and 3, and number is 0. So it means that I calculate f prime of 0. Be careful, not f prime. So here I put 0, 0, it becomes -9. And it is negative. So it means it is negative. And then I choose a number, for example, bigger than 3. Let us say 4. And then if I calculate this, 3 times 4 to the 2 minus 6 times 4 minus 9, how much is that? I don't need to know how much is that. It's clear that this is positive, yes? It is positive. And then the function here goes up, the function here goes down. Why? Because the derivative is positive, the derivative is negative. Again, the function goes up, the derivative is positive, yes? Okay, of course, here I can also teach you a trick. So here you see that I have only 2 candidates for turning points, yes? And then, of course, it is clear that when the function is from here to goes to here, it is decreasing. Otherwise, it's not possible to increase and reach to this number. But the logic is actually the other way around, because sometimes you have a lot of turning points, and I told you that the minimum might be higher than a maximum, yes? So here this point is a maximum and this point is a minimum, but still this minimum is higher than this maximum. Okay? Okay, so now everything is done. So you see that this point here, the function goes up and then goes down. So this point corresponds to a maximum, yes? And then here the function goes down and then suddenly after that goes up. So this function corresponds to a minimum, yes? So this, you need to write this down in this question. So you would say that -1 and 10 is a local minimum, a local maximum, and 3 and -22 is a local minimum. So this is today's lesson, what you need to learn is this, which is exactly a Math 3C problem. It's not Math 4 problem. In Math 4, the only thing that we can do is to change this function to a little bit more complicated function that you will not be able to differentiate it based on the rules that you have learned in Math 3C. For example, a function needs a product rule. A function needs the chain rule to differentiate. In those functions, you couldn't do this in Math 3C, but the content is exactly the same. Now, let me ask you, do you have any questions right now about how to use it? Okay, now let me give you another example. If I have enough space here, let me just do it here. So this, for example, let me give you an example that you couldn't solve in Math 3C. It's not hard, but you couldn't solve it there, yes? Let me write it. F of x equals to x e to power minus x squared. This is something that you couldn't do in Math 3C because you didn't know how to differentiate this function. Okay, let us do it again together. So I want to do this here. What should I do? According to the first derivative test, I have to differentiate the function. To differentiate the function, I need to use the product rule and the chain rule. Yes, the product rule tells me that I take the derivative of the first function and multiply it by the second function itself plus the first function multiplied by the derivative of the second function. But the derivative of x is just simply 1, and you multiply it by e to power minus x squared. And then for the next one, I need to use the chain rule, yes? This I can take it to be u. E to be u prime is the same function, but I have to multiply it by an extra u prime. So this becomes e to power minus x squared, the same function, but multiplied by the derivative of u, which is minus 2x. And then I have to simplify this a little bit because my next step to equate the derivative equal to 0 and find the roots. Okay, so it means that I have to simplify it, otherwise it is not easy to find the roots. The first term I cannot simplify it at all. But for the second term, this minus 2x will be multiplied by x. It becomes negative 2x squared. And then I have e to power minus x squared. And if you don't mind, let me factor this out. This becomes even simpler for solving the equation. If I factor this out, I will have 1 minus 2x squared. And then I have e to power minus x squared. So this is final form of my derivative. Okay. Please let me know if you have any questions here. Is the differentiation clear? Okay. And the next step is to equate it equal to 0 and find the roots. If I put this equal to 0, what will happen? This means that 1 minus 2x squared e to power minus x squared is equal to 0. Okay, now can you tell me how should I solve this equation? No one? Can you hear me, yes or no?
Yes. Yes, we can hear you.
Okay. Why you cannot solve this problem? I don't know. You need to broaden your point of view. Don't get confused because of this exponential. If I ask you read this in English, you would say this is the product of this and that. And the product is supposed to be equal to 0. So it means that this is the 0 product rule. The product of two numbers is supposed to be equal to 0. So it means that either this should be equal to 0 or the second one should be equal to 0. But now tell me, can the second one be equal to 0? E is a number 2.7 approximately. Is it possible to raise e to some power so that it becomes 0?
No.
No. So this means that this is automatically not 0. So this means that 1 minus 2x squared is equal to 0. So then this means that 2x squared is 1. So this means that x squared is 1 over 2. So this means that x is plus or minus 1 over square root of 2. So these are my candidates. These are my candidates for extreme points. How should I see that there is not a fake one among them? The only thing that we can do so far is to go and set up a table of signs, yes? This is a typical example in Math 4 in which you have the exponential function. So this is why I wrote it here for you. So you have x, you have f prime of x, you have f of x. How many numbers we got? 2. The smaller one is the one with negative sign, of course. The bigger one is the positive one. If I put these two in the derivative, it is clear that it should be equal to 0. Why? Because I myself put the derivative equal to 0 and found these numbers. So it is clear that if I put these numbers in the derivative, the answer would be 0. But I need to answer this one and this one as well. This line is the f of x line, you see? So if I want to get any information on this line, I need to refer to the original function. Okay, so for example, I can go here in the margin here. I can calculate what is this. Then what happens? It becomes minus 1 over square root of 2. I am replacing x with this number. And then I have e to power minus the square root of 2 to power 2. So this becomes how much? Minus 1 over square root of 2, and that is 1 over 2. So it becomes e to power minus 1 over 2. Let me write it more beautiful. So it becomes minus 1 over square root of 2. I will bring it down. It becomes positive, and then it becomes a square root of 2, and then it is what square root of e. So it becomes minus 1 over square root of 2e. Okay, and it is not hard to convince yourself that if I put that number, it becomes positive, this number. I don't calculate it for you again, but you can immediately calculate it in this way. But let us go here. So is it positive or negative? So I need to choose a nice random point from here so that the calculation is easy. Which point do you prefer? Which number do you think I should choose here? Of course, you can choose any one of them, but which one is the good candidate here to choose?
Minus 1.
Minus 1 is a very good one. Minus 1 is definitely smaller than this one, and working with minus 1 is easy. But be careful. I want to say something about the derivative, so I need to refer to the derivative, not the function. Sometimes I myself make mistakes. Be careful about this point. So you take minus 1 and put it here, and of course here. And then you don't need to calculate exact values here. You want to convince yourself, is it positive or negative? I don't need to care about this thing at all. Why?
E to any power is positive.
Is it positive? So it is, I don't even care about the value of x. This exponential function is always positive. So it doesn't play any role in the sign, in the final sign, because it is always positive. So I only concentrate here. If I put minus 1 here, this becomes minus 1. So the whole combination is negative. So what is a best choice? What is the best choice between these two?
0.
0. And then I go again to my derivative and put 0 here. This is always positive, so forget about that. If I put 0 here, this will vanish and I will have 1. 1 is positive. And then, for example, you can go here and take 1. 1 is bigger than this number. And if you put here, it becomes negative. And this is always positive, so the final one is again negative. So again, you see this goes down, this goes up, and this goes down. Again, none of them is a fake one. Both of them are real ones. And then, of course, it is clear that this one is a local minimum, and this one is a local maximum, yes? But you need to write it down. So the point -1 over 2 minus 1 over a square root of 2e is a local minimum. And the other point, 1 over a square root of 2, 1 over a square root of 2e is a local max. Okay, is that clear? Yes? Okay, let me just give you one more example, so do it very quickly. Number 3, the function is this. F of x is equal to 3x to the 4 minus 16x to the 3 plus 24x to the 2 minus 9. Okay, so let me just do it quickly because it is easy. I take the derivative. It becomes 12x to the 3 minus 48x to the 2 plus 48x. And then I need to put it equal to 0. So what happens? It becomes this. Okay, can you tell me how should I solve it? Because this is a third degree equation. How should I solve it?
We use the zero product rule.
But yes, before that we have to factorize, yes? So I pull 12x out. What is left from the first one is x to the 2 minus 4x. I made a mistake here. I don't know why I wrote, sorry, this is, no, let me make it smaller. So this is not 28, this is 48, because this 2 goes down, it becomes 48. Okay, so that is also 48. So this, this becomes positive 4. Yes, now it is correct. Equals to 0. But I think you can use this PQ formula, but this is a very famous combination. So this means that 12x, x minus 2 to the power of 2 is equal to 0. Okay. Yes. And then you see that how many numbers I get. By the zero product rule, one of the numbers is 0. And the other number is x equal to 2. Okay, and then I go to draw this sign table. I have x, I have f prime of x, and I have f of x. Two numbers, the smaller one is 0, the bigger one is 2, so these two numbers is always 0, and then I need to find these numbers here and there. I need to put these numbers into my function. Putting 0 is super simple. These are gone, and minus 9 is left. And then if I put 2, let me calculate it here. So f of 2 is, so this becomes 16, it becomes 48. The next one is 8 times 16 minus 128. And then 4 times this is 96, and then I have minus 9, yes? So it is minus 80, and this is 16, and this is 7. Yes, so this is 7. Okay, and then I need to know the signs here. I choose a random number before 0, it is minus 1, it's a good number. I put it here. If I put minus 1 here, this becomes minus 12, minus 48, plus minus 48. So definitely this number is negative. I don't care about the value, but I just want to know that this is negative. If I choose a number, random number between 0 and 2, the best choice is 1. I put it in the derivative. It becomes 12 minus 48 plus 48. This is gone, so 12 is positive. And then if I go after 2, let us choose 3 here. Okay, so that is a little bit problem. I put 3 here, f prime of 3. Of course, it is clear that this is also positive. I can use this trick. You see, this is another form of my derivative. If I put 3 here, it is easier than to put it in this form. Because if you see, this is the factorized form of my derivative. So I can say that this is also my derivative. There is no difference between them. And putting 3 here is much simpler. So it is positive. So again, it is positive. Now, finally, this is an example that you see that one of these are the fake ones. That's the terrace point, yes? Because this goes down. Here, this goes up, and again, it goes up. So one of them is a minimum. You see, this one is a minimum. Yes, this one is a minimum, but this one is a fake one. It's a terrace point. So I would say that 0 and minus 9 is a local minimum, but 2 and 7 is a terrace point. Okay, so sometimes you see that you might have a real fake one. So sometimes, and so this is not guaranteed that as we predicted by that geometric picture in our head. So sometimes if I have roots, one of these roots, or even sometimes 2 of them might be the terrace point. So here I have 2 roots, but I have only one extreme point. So this function doesn't have any maximum at all. It's interesting, yes? This function has only a local minimum. Of course, there is no time, but later I can start with drawing the graph of this function that you can see how this will work, okay? So hopefully you learned. So what I just mentioned here is nothing new at all. Everything should have in principle be covered. I remember I myself covered it even in more details. But in principle, this should be covered in Math 3C. The only thing that this is new for you, in principle, I should start only with this example, but as I promised, I will not count on your knowledge from Math 3C. This is why I reviewed everything. So if you can solve these 3 problems, it means that you understand everything in this session. Any questions? We still have time, yes or no? This session is longer, yes?
We have 20 more minutes.
We have 24 minutes. Okay, 20 more minutes. Okay, so let me see if I can draw the picture of this function for you by GeoGebra. So let me just stop this sharing. And now you can see this. So I just put the function here, and this is what you see. And then you see here, interestingly, what we predicted was correct. This point corresponds to that terrace point. You see, this is 2, exactly at the point that we predicted. We have a terrace point. And then we have only one local extreme point happens at 0, and the value is minus 9. And that is exactly the one that we predicted. So you see, this function doesn't have any maximum point at all, as we predicted. So, and by the way, this is very important because, for example, if you draw the graph with your function, I don't know, this is something strange when you see, but based on mathematics, you understand that this function should be a continuous function, so this should not be a real graph. So this tells you that, okay, if you want to see the real picture, you need to zoom out to capture the essence of the graph of the function. So that is the point. So we realize that, you see, before 0, the function is decreasing, and when it reaches to 0, it is a turning point, it goes up. And then when it reaches here, that is not a maximum or minimum. This is just a terrace point, and it will continue going up again. So that is the graph of the function. What we calculated squares with what we see in this real picture. Yes? We can also test, for example, the other function. I don't know, have you written something down or not? Let me write this exponential function. That was also a very interesting one. So let me delete this, and then I can just put the other function. So the other function was y is equal to x. I think in GeoGebra it should be exponential function, yes? Or I don't know. Yeah, okay, I have it here. So y is equal to x, and then this is e function, and then this is to power, and then I have minus x to power 2 again, and then this is my function. So this is the function that you see the graph. So let me zoom in a little bit, because this is the interesting part. Yes, here you see that I have 2 points. One of them is the minimum point, and one of them is the maximum point. So if you see here, this number is actually 1 over square root of 2. Yes, so let me, for example, we predicted that the maximum point, if I can write a point, so 1 over the square root of 2, and then another one is, sorry, it's 1 over the square root of, and then if I calculated everything correctly, it was this number. And then let me see where this point is. So yes, I have made it very small. If I go inside, you see this little dot. Let me go to the setting, make it a little bit bigger for you. I increase the size, and let me make it like this. Okay, and then I will come back. So you see exactly this point that I got using my calculation is exactly this point, which corresponds to a local maximum point. Yes? So it was not easy at all to guess that this very strange number should be the number corresponding to the maximum point, but this, I just got it with my calculation. If you refer to your notes, you will see I got this by calculation, and I would check it. I immediately find that this is the extreme point. And the numbers with negative signs, it is clear that this is this minimum point. Okay, so this is a very important tool. So it means that assume that you didn't know the graph of the function, but you know that this is a extreme, this is a local maximum point, and this is a local minimum point, and it is easy to see that this function passes through the origin, because if I put x equal to 0, it becomes 0. And of course later you can understand that this point is an inflection point. So using these three, this part of the graph is completely clear qualitatively. You see, it is easy to see that this graph has this form. Why the function behaves like that, we will probably study later. That's called the notion of asymptotes. So this x-axis is called the horizontal asymptote of the function, which is also included in this chapter. This is a very, very long chapter. So you need to study harder and harder, put more time on it, because otherwise you will lose. This is a very long chapter. And the next one is also complex numbers. That's also very essential and very long. Okay. So I wanted to start to talk about the second derivative test, but I think it would be better to stop here. That was a lot of information, and probably you are still stressed a little bit about the exam. You don't need to be stressed. You just solve the problems in the book, and then you're on the safe side. So let me just stop this video first of all.